Question on Wednesday is gonna be also you or Melissa because she told me 27 is gonna be you, but I don't know for Wednesday.
We hope she'll be back on Wednesday, but I will have to check with her.
All right. I'll put you on the calendar invitation anyway, so
Sure.
all good.
No,
All right.
I think we can start because people sometimes can be come after 10 minutes and I don't want you to wait that much long. And
got it.
yeah, whenever
Sure.
you feel free, like floor is yours. And
Got it. Sure. I'll share my screen.
yeah,
Hey, I hope you guys can see my screen now.
yeah, we can see.
Awesome. Shoots. Oh, okay. Cool. Yeah, so I guess you have a lot of lectures before to this where you guys explored a lot about zero-knowledge cryptography starting
Just a
from,
question.
sorry.
Just a, yeah, we can see your camera. Like
Oh,
I think it's gonna be better for everyone.
No, like if you're free, if you don't, that's okay.
oh, okay, no worries. Okay, I hope you can see me now.
Yeah, right now it's
Yeah, all good.
okay.
Awesome. Cool. Yeah, so I hope like you guys have been reading a lot about CK, starting from hashing functions. What I heard from it, it's you guys explored a lot about hashing functions and KGG, and actually writing some circuits with Circom. Then you also got some lectures from Asto about NOR and all those things. So maybe this is your last week or the second last week. And in this week, we'll be trying to focus more on how to apply all those things which you have learned to actually build ZK products or ZK applications out here. And zkVerify itself is a very big part of it. So I guess you guys knows about the two parts of ZK. One is the proving and one is the verification. So we try to do the verification part out here. Uh, and we have partnered with multiple of prover networks who help us to do a lot of the proving things as well. Yeah, so to start with, just a brief intro about myself. I'm Arman. I'm the solutions architect at Horizon Labs. Horizon Labs is the main research company behind zkVerify and the Horizon chain. And we have been doing a lot of ZK specific research. If you have heard of Poseidon 2 hash, that's also one of the things that our researchers contributed to. So we have been in this field for a long time now. Cool. So today's agenda is we'll talk about what is zkVerify. Obviously, that's the whole thing. We'll understand how it works, the whole architecture. But I would like you to focus more on why do we need it, and then I'll show you some use cases and then how to actually use zkVerify in your real applications. Because just doing theoretical level stuff is not what I believe in. I try to make things much more implementation friendly. So I'll try to give you some real life use cases and we'll try to actually write a circuit and then try to verify it on zkVerify. Cool. So let's start with the actual definition of zkVerify. There's nothing specific, but as I told, in the whole ZK pipeline, we have two things. One is the proving layer and one is the verifying layer. And proving is kind of the most computational expensive layer, where you actually do all those field elements, hashing, elliptic curves things. So it's basically it's the kind of the slow process, and verification is kind of the easy process to do. But when you do it in a blockchain, think of any EVM blockchain, take Ethereum, any L2, or even Solana, or any Cosmos ecosystem chains as well. Uh, all those system, all those chains are built for some specific amount of computation. If we try to do anything over from that, we start getting a lot of lags. They are not too much ZK competition friendly. We don't have a lot of field elements implemented there. So Obviously, verifying zk proofs on all these chains are very, very hard and are not very, very efficient. So what we have done at zkVerify is we have built a particular blockchain, and the only thing this chain does is just verifies proof. It doesn't hold any smart contracts. It is not a general programmable blockchain. It's kind of an app chain. It's a layer one. You can say it in a layer one app chain, but the only thing this chain can do is just verify proofs. And we have support for multiple types of zk proof. So Sitcom, the Graph 16 one, Noir, Ultra, Honk, if you're like obviously you have heard of. Then all the ZK VMs, we support almost everything. Whatever you have, whatever is in the market, whatever you're trying to develop with those things, we already support it. So we're trying to basically build the universal verification layer for zero knowledge proofs. And why this is needed, because when you try to verify proofs on EVM chains or for any Web3 applications, uh, there's a lot of inefficiencies, which we'll explore more in the further slides. And we're trying to solve that particular purpose. And this is just so not so cool definition of zkVerify is that we just verify zk proofs. We don't do anything else. And if you guys have heard of substrate framework, so it's a term from the Polkadot ecosystem of how you build chains. So technically speaking, zkVerify is a substrate-based blockchain, L1 blockchain. We are a solo chain. We are not related, or like we don't have any connections with the Polkadot ecosystem. We host our own set of validators, similar to Ethereum or any other L1, and we try to do everything on our own.
Um,
And
I'm, I'm sorry, can I ask you what's substrate framework? I didn't understand that.
okay, so have you heard of OP Stack any chance?
What stacks? Which stack? I'm sorry, I couldn't hear it.
OP Stack.
Oh, yeah.
Yeah. So OP Stack is a way of building L2s, which is build by optimism, right? So think of Substrate as a similar framework built by the Polkadot ecosystem. And it basically makes easy for you to develop blockchains. So when you think of a blockchain, there are multiple things involved, right? Networking, state management, everything. And what Substrate enables you is that you can build all those things. You can just focus on the app logic of what your chain actually do. And while all those state management and networking is handled by the framework,
Oh, I
so that
see.
you don't have to indulge in that.
Like in
Exactly.
Cosmos, I believe it was like interchain protocol or
Yeah.
something like that.
Kind
Something
of.
okay, like that.
Yeah.
Thank you very much.
Yes. So there is one more term I would like to focus. I forgot to add it to the slides, but there is something called as palettes in Substrate framework. And these palettes are basically smaller parts of the whole blockchain. So in Polkadot, what happens is balances like the ERC20, as we talk about in Ethereum context, the ERC20 tokens. In Polkadot, this is called as balances, and balances is written in a specific palette. So everything is broken down into small pieces of code, which is known as palettes. So in zkVerify, what we have done is, as I told you, we support multiple proof types. We have built palettes or specific logic for every particular proof type. So the verification for a Graph 16 proof is different than the verification of an ultra honk proof. Like the logic is totally different. So that's why Substrate is one more much more powerful thing for us, because it enables us to build all this palette specifically for each proof type. So this was more about what is zkVerify, but why do we actually need zkVerify? We have all the chains. We have smart contract verification systems for all the proof types. If you have explored the zkREPL framework, so when you write a circuit over there, instantly you get a smart contract as well, which you can deploy on any EVM chain and verify your zk proofs. Then what's the need of zkVerify? And this is not the main reason, but one of the very affluent reason of using zkVerify is the cost of the proof verification. So on Ethereum, not right now, but when the gas spike happened, maybe 2, 3 years back, the verification cost of a single zk proof was ranging from $20 to $30, and even it went to $50 at the hike of the gas. So this is one of the big reason why we need zkVerify, because as we go to the next stage of the cyberpunk or the privacy world, we say, we'll see a huge influx of proofs for everything. Let it be identity, let it be DeFi, let it be AI. And all the EVM chains are not able to handle all these computations. So zkVerify is trying to solve this issue in the whole ecosystem. And we're trying to lower down the proof verification cost for ZK developers and products. So we'll dive a bit more into the exact issues that we face. So you all have heard about ZK VMs. If not, the easiest way to explain ZK VMs are like you have build circuits with Graph16, you have build circuits with Noir, right? And one thing in both the things in both the ecosystem is that you have to write their specific language. So if you're dealing with Circom for Graph16, you have to learn the Circom language, and it only support the field element type and what are the operators. Everything is different. Even if you want to do a greater than operation, you have to write a whole, and you have to import a whole new circuit, then rewrite it again. And there is a lot of the DevX is not very good to say. Noir is much more efficient in terms of DevX when you compare to Sitcom or the Graph16 one, where it is very similar to Rust. But still, Noir has some kind of its own way of doing things. For example, hashing, for example, signature verifications, all those things. And this is one of the biggest hindrance of ZK not being mainstream, because developers are not able to build on this stacks, right? Because all these languages are domain specific. So there's a very steep curve of learning these languages and then implementing it. So ZK VMs are a new way to handle the ZK issues. And how they do is you write your logic in Rust, at least right now. And in normal Rust, you don't need to learn any specific Rust for ZK. You can write your specific things in Rust, normal Rust, and you can then try to say which thing will be private and which will be public, which particular variable will be private and which particular variable will be public. And then you can do a lot more of computations. So if you have heard of the latest trends in the zkVM space, so SP1 has been verifying Ethereum blocks almost real time within 12 seconds. There is one more Stu-based verification, and they are verifying Bitcoin blocks as well. So all those computations are very big, and they cannot be done in normal snark proof, which you have learned till now. And they have to be implemented in a Stark proof basis. And zkVMs are the best way to do it, kind of like. But the issue with zkVMs is that they produce Stark proof type, and verifying them on EVM chains is not at all efficient. And here are some reasoning which I want to give for this. The first is the Stark proof size is like 7.4 megabytes, and that's the average. For some, it even process 20 megabytes as well. And the current Ethereum block size is like 150 KB. So you think of it like, how will you put this particular proof inside a block to be verified? So it's not at all efficient. You can do it in some manner, like split the 7.4 MB into multiple blocks and just divide it. You can get a lot number of blocks to send specific chunks of the proof and then verify it. But that's not efficient. It will take a lot of gas and all those things as well. The other thing, and the more specific thing for Starks, is there is something called as FRI. I don't want to go into detail what FRI is, but it's very computationally expensive. There's a lot of hashing, there's a lot of Merkle tree inclusion, and a lot of things happening over there. And right now, if you want to do it on EVM, it's not, I would say it's not even possible in some EVM constraints as well. Because the maximum block gas, like the maximum gas that you can use in a block is 30 million right now. and the stack proof cannot be verified in a single block because of this. So again, you can split the whole computation of verification into multiple chunks of blocks, but again, it's like it's not the best way to do it. And the third thing is no precompiles. So with snarks, or the Gross16 or ultra plonk, ultra honk, with the Noir language, we have some kind of efficiency because we have precompiles in the EVM ecosystem. What I mean by precompiles is, uh, for example, doing a hashing function on EVM is not efficient. So what happens on the background is there's a particular Ethereum node which takes your particular input, hashes it, and give you back in the smart contract. And for this, you pay some gas to the node. This is not the best example, but an easy way to make you understand. So there is some kind of off-chain computations also done in stocks, but stocks, at least till now, we don't have the precompiles for that. And that's one of the biggest drawdowns for stack verification on EVM chains. But in zkVerify, the best thing is we do support stack verification natively. So you don't have to do it anything of your own. So you don't have to care about the proof size. You don't have to care about the amount of computation to do on chain. Everything is handled by us because we have a substrate chain which is customized just for this purpose. It's very, very efficient. And this is just a depiction of how it works for stocks. So there are multiple proofs. For example, this is a proof chart. So think of a single proof is spread into multiple proof charts previously. And then we compile all of this into a single proof. And without zkVerify, what used to happen is we convert this compressed proof into a Gross16 because we know that Gross16 is verifiable on chain on EVM. And then we verify this Gross16 proof on chain. So there's an extra step you can see out here. And when you do with zkVerify, you don't have to do it. You can just directly verify the compressed proof. You don't have to wrap it to a Gross16 again. So you are removing a one whole layer of computation around this. And based on the current mainnet fees of SV1 proven network, this straight up gives you an edge of more than 30%. So currently, if you do it without zkVerify, you would be spending around 0.3 proof for proving something on the mainnet. And when you do with zkVerify, you just do it within 0.2 proof. So that's 30% of 33% of exact proving cost efficiency. And this is one of the main reason why this whole product came up. Uh, as I told, the Gross16 proof verification was around $10 to $15 at a time. But when you do it on zkVerify, it comes down to $0.008. It's like very, very cheap. It's like 1000x much cheaper than ETH and then 100x cheaper than L2. So even if you do in L2s, for example, Base, Optimism, Arbitrum, it'll still cost you around $0.1. But if you do it on zkVerify, it's like $0.008. So for an individual dev who is doing maybe 10 proofs a day, maybe this is not something very significant of saving. But when we're talking with DeFi protocols, so if you've heard of Singularity, they have been a good partner with zkVerify and they have been building a lot of cool stuff. And they have been verifying uh, at some time like 100K, 200K proofs per day. And when you compare this particular saving, it like ends up saving 50K, 60K per day of proving cost, verification cost, sorry. So this is the main reason why we have zkVerify. And then we'll explore further the whole architecture and all those things. But before moving forward, if there are any questions on why do we need zkVerify and all those things, I need to clarify that. Any questions, guys?
I think no. In the chat, someone asked that, are there any L2s using zkVerify?
Uh, So we have connected L2s. So on the testnet, we have around 6 to 7 L2s connected. So we have Arbitrum, Optimism, EduChain, Base, even Horizon is in L3 right now. We've connected all those things. On mainnet, we have Base connected, and there are plans to integrate much more L2s in upcoming few weeks and days.
Thank you.
Okay.
Augusto asked, what do you know about Stellar, like whether they're gonna implement or not?
Sorry, I'm not sure about the question.
Uh,
Like, is it about the integration of zkVerify with Stellar?
yeah, I believe so.
Yeah, so we have been talking with a lot of non-AVM chains as well. And the first one, at least for now, the priority is Solana. We want to do that first, but we do have talks with move-based chains like Sui, Solana, Stellar, Cosmos-based ecosystems as well. And because we are chain agnostic and we are not having a particular environment like EVM, it is very easy for us to connect with chains. So if you're building anything on Stellar or something, just ping me or Militza up. We'll connect you with the engineering guys and maybe they would just help you make a bridge within few weeks. Cool.
I think that's all. That's all the
Cool.
questions. Yeah.
Cool. So, okay, we'll move forward to the architecture of how we build zkVerify and how it works. So, as I told, it's a specific L1 chain of its own. So it's not an EVM chain. It's not an any ecosystem right now. It's a very separate chain, only meant for verification. And in normal chains, you interact them with RPCs. The same thing with zkVerify as well. We have an RPC URL, uh, and you can just send us proofs through it. So in normal chains, you send us the smart contract interactions. You want to make a swap. You want to buy some tokens, all those things. But for zkVerify, you can only do three specific things. The first one is obviously the sender's proof to verify. So as I told, we have interface for multiple proof types. Here it's RISC-0 Glock16 noir, but we have added like 4 or 5 more out there. So every particular proof type has its own interface. You can interact with it and send proofs for verification. The other thing is obviously transferring the balance. So zkVerify has VFI token as its native token. So you can own the VFI token and you can use it to pass it around. And for verifying these proofs, you need the VFI token as well. And the third thing is the governance of this chain. As it's an L1 chain, so it has its own governance and all of those things. So that's also a part of it. So now coming part to the technical layers of how it works. So we have an interface, common interface used by all the proof types. You send us the proof, and then, as I told, we use something called as palettes, and these are nothing but smaller code snippets for each proof type on how to verify those proof type. So this interface take your proof, passes it to the respective palette, which has the logic to verify this particular ZK proof. And then once it is verified, it is included in the block. So as it's any blockchain, we also have blocks. So it is part of a block now. And then as it happens in any chain, the block is included, the block is finalized, and then some more events happen as well. So here, once your proof is verified, it is now part of the block. And then after 6 seconds, it is finalized as well. So the block time for zkVerify is 6 seconds. So once you send a proof, within 6 seconds, it's get included in the block if it's a valid proof. And then this particular proof is then passed to something called as receipts aggregator. And why we need this component is because we want to connect zkVerify to multiple chains. As I told, we have been working with multiple L2s, Ethereum obviously, and Ethereum L2s, and then Solana and other non-EVM chains. We want ZK product from any ecosystem to use zkVerify for verification. So without this particular component, it's not possible for any other chain to know if a proof is verified on zkVerify or not. So this particular component lets other chain knows that yes, this proof is verified on zkVerify. So how it works is for every proof you verify on zkVerify and you want to emit it to a chain, while submitting it to the interface, you tell us the chain ID where you want to submit the aggregation to. And what we do is we verify your proof on the main chain, and there are a few conditions. Once they are met, it is now relayed to Ethereum, any other to Solana, any other chain you want to. So this is I'll say the biggest USP of zkVerify chain as it is, because we can connect ourselves to any ecosystem. We are ecosystem agnostic to say. So if you're building anything on any chain, you can just use zkVerify out of the box to verify it. And you don't have to move your smart contracts to any specific chain which we support or even our own chain. You can just have your logic, which is already implemented, and you can just plug your proof through zkVerify. So
Can I
this
ask,
is the main architecture. Sorry.
I'm so sorry. Can I ask two questions? It is about this, so that I wanted to ask.
Sure.
The first one, I'm just trying to understand the process. Like, in zkVerify, are there nodes that try to verify different type of proofs? Like, does node each node try to verify different type of proofs, or all of them try to verify the same one? Like,
Yes. So all the nodes have the logic to verify all proof types. And whenever you send a proof to the zkVerify chain, each of the validator, which is so basically it's a proof of stake chain. So at a particular timestamp, only few validators are active. So out of 30 validators, maybe 5 or 6 are active at that particular time. So it's basically an election-based process where
Yeah.
every 6 hours a new set of validators come in. So when you send us a proof, so all these active validators will verify that proof. Each validator will verify that proof.
Okay, and I want to ask one more thing about receipt aggregator. I think I understood wrong, because I thought that if I verify something, I can just take the, block ID and where is the verification, and I just show that. Why do I need something like this? Like, I don't know if I understood completely wrong, but
Okay. Yeah. So if you want to do it in an off-chain level, obviously you can just verify with the block number and your transaction number as well. You can just say that this transaction has my proof, which is verified on zkVerify. But without this receipt aggregator, how will you connect it to a different chain to say?
So what does aggregator produce? I didn't understand. For example,
Yeah.
I have a smart contract on Ethereum and I
Mhm.
verify something with zkVerify. What does this aggregator gave me for my contract?
Yes. So I'll show you more further of this, but
Okay then.
later.
I'm sorry.
But how it works right now is for each proof which is verified on zkVerify and needs to be emitted to a chain, you'll get a unique hash of it. And this hash is basically it includes everything like which proof type it was, the whole proof of which is verified, the public inputs and everything. And then you can verify that on any smart contract on Ethereum. So how it works is every aggregation has its own unique ID, and then you can check if this unique ID has the matching proof details which I want to verify or not on your EVM chain.
Okay, thank you very much.
Got
Sorry
it.
to
Okay.
interrupt.
If anyone has more questions on this, because this will be crucial to understand the next slide. Okay. So as a developer, this is the workflow that you would be working on. So you have a proof generating system. It can be your ZK app, it can be your ZK rollup, anything. And then you generate your proof, and then in the step one, you verify it on zkVerify. So this is the zkVerify main chain. We verify your proof, And then, as I told, at the end of the pipeline, it's get aggregated to the Ethereum chain. So as you can see, in step number 2, the proof is aggregated and the aggregation is passed to Ethereum. Now, when the aggregation is passed to Ethereum, we do emit some events at the zkVerify chain on which particular aggregation ID was your proof part of. So in a proof generating system, then this can be a front end or back end, anything. Then on the Ethereum chain, what you can do is you can check for this aggregation ID if this proof and inputs are matching or not. So basically, you'll get a hash and the aggregation ID out of the zkVerify chain to an EVM chain on or any other chain you want to verify on. And then you can verify if the aggregation ID actually contains your proof and inputs or not. So it's a Merkle proof. I'll show you further in the examples, but this is what the exact system is like. So, and we have tried to make it much, much simpler for you. So we have something called as a relayer service, and we don't want developers to get into issues of connecting with RPC, handling tokens, the VFI tokens. So we have built an API service, which I'll show to you right now. And this API service you can just submit proof through it. And then at the end of it, you'll get the aggregation ID and the leaf for your proof. And then using both of this, you can verify on Ethereum or any other chain that is your proof actually verified on zkVerify or not. So that's the usual workflow that you'd like to build with zkVerify. So the next slide or the next thing is about having a demo. I'll show you a demo. Before moving to it, any questions on the workflow?
Yes, I have a question. I just wondered, is the output of the verifier the same regarding the different types of schemas like Graph 16, PF Planck? Like, is it a way to see which type has been used by looking to the outputs? I don't know.
Yeah, yes. So the output which is sent to all these chains, it is basically hash, and the hash is basically a hash of everything that you have. So it's a hash of which proof type you used, Graph 16, Ultra Honk, Plonk, Risk Zero. Even for Risk Zero, we also have different parameters like which version of Risk Zero you used, then the public inputs of it, and the proof of it, and everything. So everything is actually a part of the whole leaf, which is sent to the smart contract. So you can check every detail of the proof verified on the smart contract out here.
Okay, so you unify the outputs by hashing it.
Yeah.
Okay. Thank you.
Cool. Any more questions? Okay. I'll share a demo of how to actually do zkVerify stuff. It's not something very fancy, but it is something very, very simple and would be easy for you guys to understand. Let me just spin up. So have you, I guess you guys have explored zkRapper, right? Where you write the SECOM circuits and generate the proof and all those things. Cool. Share my screen. I hope you can see my screen now.
Yeah.
Okay, cool. Yeah, so coming back to the first lecture, maybe. So we have the example circuit at zkRipple. So whenever you load zkRipple, this is the example circuit that you'll get. And when you compile the circuit, you'll find few things out here. The main.wasm and few other artifacts. And when you generate a proof, you would need this, but as you're just trying to verify it, let's do it something around. You can click on graph 16 to select which proof type you wanna prove in. And here you'll get all the important files for verification. So, and even generation of the proof as well. So you have this main.graph16.html. So you can use this thing to show. You can use this particular thing to generate proof locally on your browser. So if I give an input of 5 and 77, if I want to generate a proof to say, as you can see, I generated a proof. And then I can verify it locally only on my system that is it's a valid proof. But we want to do this on zkVerify. So there are a few things that we need to download from here. So for every particular circuit you write, there will be a file called as the vkey. This is the verification key, which is unique to a circuit. So based on how you have constructed the circuit, the vkey will be compiled by the Circom compiler. So we'll need this. Let's download that. So, okay. And then, as I told, we have something called as relay service. I'll try to spin up the docs, show you something. Okay. So the old way or the kind of the advanced way of doing verification with zkVerify is by doing it through zkVerify JS. So it's the OG verification stack that we have built. And how it works is you need to give your seed phrase for your wallet, which has VFI tokens. And then based on the proof type out here, you can try to read the proof data, which you have downloaded, like the wiki, the proof and everything. And then as you do it in any other blockchain, you need to create sessions and send transactions to it. Out here as well, you create a session and then you call the verify transaction. You give it which proof type you want to verify. And then at the end of it, the proof data as well. So these are few things, but to start with, I would recommend you to use the relay service. And this is the REST API, and this is built by Horizon Labs, the research company behind zkVerify. And Relay was meant to be making the developer experience much, much simpler. And we do it through Web2 APIs. So you don't have to handle tokens, you don't have to handle anything. How it works is you just make an API call to the testnet API we have out here. And then you can just verify proofs, start, like you don't have to do anything else. So I'll show you a few examples of how to do this. We even have these Swagger documentation. If you want to explore more about this, you can go onto this links and try to do that. But yeah, I'll try to show you how to do in Sitcom. So we even have a tutorials repo as well. So if you go to zkVerify, you'll find a repo called tutorials, and there you have zkVerify JS as well and Relayer as well. So we have a few examples here. I'll try to go through this, and I'll try to go through the Sitcom one because that's the easiest one to say. Okay. So we have some artifacts already here, which I generated previously, and I used it. So this the similar thing which you will download from zkRipple out here, the wiki and all those things. So it's the same wiki for some different application. Now, out here, when you generate a proof, you can see you have pi A, pi B, pi C, and all those things. So I have a similar proof. I have pi A, pi B, pi C, protocol, and curl, all those things, and the public JSON. So we just need three things out here to verify something on zkVerify. The first thing is the verification key for the circuit, the proof file, which actually contains the zk proof, and the public.json, which contains your public inputs. So both the circuits are not same, obviously. This circuit has two, this circuit has one. So this is a different circuit which I was building and trying to verify for. And now I'll show you how to do it with Relayer. So as I told, it's a API stuff. Maybe I'll zoom it a bit. So how it works is you have an API, and to use this API, you would need API key. If you want an API key, just DM me or Melissa, anyone. We can give you an API key to start verifying proofs on zkVerify. And we're just parsing out the proof, the public inputs, and the verification key from the public files that we have stored out here. So if you go to assets, Sircom, you get the proof, public, and wiki. So you are just importing it here, trying to read it from those. And then you can remove this part. This is something more advanced, but we're just trying to construct the parameters of the proof, which we have read, the public signals of the circuit, which is in the JSON file. This wiki, like you can directly pass the wiki as well, but this is a more efficient way to do it. We hash the wiki through a particular process and then we pass it as well. So you can do that as well. And you can give the proof type. So that's the first thing you need to pass, which is which type of proof are you trying to verify with zkVerify. These are some more advanced things which you can explore later. And then the proof options. So like for Grok16 proof, zkVerify support multiple variations of it. So whatever you generate through zkRPL is Snark.js library based and BN128 based. But there are some other libraries as well called as ArcWorks. I can show you that. So this is ArcWorks is basically a Rust library, a modular library to write ZK circuits. They do support Grok16 and multiple proof types out here, so you can see it here. And like the Grok16 implementation of ArcWork is a bit different than Snark.js. So we also support that, so the library can be that as well. And this is the parameters what you want to verify. And then what you do is you use Axios. I guess you guys are familiar with Axios, but if you're not, it's just an way to make API calls to a backend service. So, and you can post it with the API URL and the API key and passing these parameters that I want to verify this proof. This is the proof type. This is the chain ID. So as I told, we can give the chain ID where we want to send the attestation or the leaf to it. So that's one thing. So maybe I'll just change it to Sepolia for now. And then you can see the proof data and all those things. So, and out of it, you instantly get a message that either the proof is success or not, which means the proof is valid or not. And if it's valid, so then you can wait for different kind of messages coming through the zkVerify chain that if the proof was included in the block, if the proof was finalized, and if the proof was sent to the destination chain or not. For here, it's the Ethereum Sepolia chain. And then this is the same thing. And let's try to run this. And let's see if it works. So as you can see, we get a job ID and we got an optimistic verify success, which means that yes, the proof is a valid one, but we are waiting for it to be included in the block. So as you can see, the object is submitted, which means that the proof was submitted to the chain. It was included in the block and it was aggregated. It was finalized as well. So the blockchain things, the core components things are done. Now we need to wait for the aggregation. Now the aggregation is a bit tricky to say because it depends on the traffic on the chain. So think of there's a lot of people who wants to send proofs to Sepolia chain. So aggregation will happen very, very fast. And if there are not a lot of people, we wait for a specific time. So think of right now, not a lot of people are interested in sending proofs to Ethereum Sepolia. So we have a cutoff time of 2 minutes. So either we have a lot of traffic or we have 2 minutes. And if any of those cases fails in, we'll send a proof or send an aggregation to Ethereum support. So we are just waiting for it. So let's wait. And in between, if you have any questions, you can ask. Yeah. So as you can see, it was aggregated, and we got the Graph16 proof type, we got the chain ID, we got the transaction hash. We can try to verify this as well. So, as you can see, it was verified 2 minutes ago, uh, and it was successful, and it will have the whole proof, like the ABC part, the wiki, the public inputs and everything. And it also holds the domain ID or the aggregation stuff which we want to do out here. And the next interesting thing that I want you to focus on is the aggregation ID and the statement. This is the two things which I told that the chain will give us to verify it on other chains. So the statement is basically a hash of all the details that is part of this particular proof. So I can show you how this particular thing is built. Yeah. So when you submit a proof to zkVerify, how it works is we hash the verified context, which is like which type of proof it is, the V key or the verification key, the version of the proof. As I told, for RISC-0, we have different kind of versions. And then at the end of it, the public input bytes. And this is unique for everything. So in this, I can try to verify, or like I can try to say that using all these components, I'll get an hash, the leaf digest, which is out here, leaf digest in the statement. And using this, I can regenerate the same thing on any other EVM chain and try to verify if this is the exact same thing or not. And I can try to check if the same proof was verified on zkVerify or not. So we'll try to check that on the next stage of this tutorial. But if you have any questions, this is like the core part of using zkVerify. This is how you use it end to end of how you make the API calls. As you can see, it's very, very easy. Nothing like you can even pass it to ChatGPT and it can write the whole code within the first prompt itself. That just write parameters, what you want to verify, just make an API call. That's all. No need to make RPC connections, no need to sign transactions, make transactions, all those things. So it's very, very easy. Any questions before moving ahead? Cool. Okay. So we'll move ahead to the aggregation side of things of how do you verify it with zkVerify on any EVM chain. I'll try to demonstrate that now. Before moving there, just a minute, I'll reload the remix portal. I'll reshare my screen. I hope you can see my screen now.
Yes.
So, good. Yep. So we've came to remix because we want to prototype fast the whole thing. I'll try to zoom it a bit. Okay. So over in the docs, you will find the contract addresses in specific chains. So we can go to supported networks. On mainnet, we only support base for now. As I told, in the upcoming days, you will see a lot more. On testnet, we do support a lot of chains, as you can see. And out of this, we are doing for Sepolia. So as we can see, let's get the proxy contract address. You would need that. This is the proxy contract address. And then out here, we have deployed our contract, obviously, on Sepolia, which keeps track of every aggregation. And then you can make a function call to our contract to check if your proof was part of that aggregation or not. And we pass the domain ID, aggregation ID, leaf, and everything out here. So I'll try to demonstrate it, and then I'll make you explain what each thing out here does. Okay. We'll do an Sepolia for. If I deploy, okay. So I've deployed this contract. Now what's happening inside this contract is we are passing the aggregation contract address, the address where zkVerify is storing all the aggregations. And then we want to verify if this domain ID has my proof or not, or has my leaf or not. So we can pass it here. I'll just pass the aggregation contract. Domain ID is 0 for Sepolia if you want to check how it's calculated. So go to learn section over here on the proof aggregation engine. We have domain management. And for testnet, as you can see, for Ethereum Sepolia, it's 0. So use the bot one. Now, the aggregation ID which we got out here is this one. I'll just copy paste it. The leaf, this. So, lot of oops. Okay. And then the last part is the Merkle proof. You'll get everything within the events from zkVerify. Just need to rewrite it here. Cool. So we have sent it all, and that's option. Cool. As you can see, this particular transaction passed without any errors. Uh, so there was no error and it passed perfectly. If I change the aggregation ID, for example, if it's an invalid proof, you'll say it will revert the whole transaction, seeing that this proof was not part of this aggregation. So this is how you basically interact with zkVerify, and we do also a test on any other blockchains as well. So that's the whole workflow of how you use zkVerify and then try to uh, make it chainless with contacting any other chains through zkVerify. Do we have any questions?
Do you have any like tutorial like code examples on GitHub so that we can check?
Yeah, yeah. Wait, let me reshare my screen. Yeah. So the best resource that I can share you is if you go to zkVerify docs out here, and if you go to the failure proof of out here, so over here you have all the snippets for each proof type which you want to try on, and you don't have to actually write any code out here. You just like whatever I showed out in the VS Code thing, it's exactly the same thing copy pasted from here.
Oh, I see.
So you can just go to this page and try to copy paste each and every part of it, and at the end of it, you'll get the same code.
Okay, thank you.
Cool. Okay. Okay. So maybe we'll move to the last slide or the last section of what are we building with zkVerify specifically. So as I told, zkVerify is meant specifically for handling volume of proofs in a much more cost efficient and time efficient manner. So these are the two use cases that we have been researching on, and I've built both of those things in the past 2-3 months. The one is proof of geolocation. So how it works is, think of, you want to share that I am in a specific state, specific city, so specific country, without actually, yeah. So basically, mobile proving can be done. So you generate your proofs on any mobile phones using MoPro, and then you verify it on zkVerify. zkVerify is a chain, so you can connect it through desktop, mobile phones, Raspberry Pi, light clients, anything. Uh, so yeah, it's not dependent on your device.
In the example that you gave, like a photo is actually captured an iPhone. Have you used the Apple's enclave?
Sorry, I was not able to hear you.
In the second tweet, you said that in the tweet it says that it used Apple Secure Enclave. Isn't
Yeah.
it for like a bioinformatic data or something like that? No?
Yes, I'll explain how both of these things work, just a bit of context around it. So both of these things are mobile based, where we generate the proofs on the mobile phones, and then we verify it on zkVerify. And the whole ideology behind this both projects are that mobile phones is right now the biggest consumer electronics out there. And if you want to onboard the next masses to Web3 or CK, mobile phones are the way to go. And we wanted to do some kind of research or POC on that side. So the first one is built with something called as MoPro. So MoPro is an effort by the PAC team from Ethereum Foundation. And those guys have built a very specific library for generating zero knowledge proofs much faster inside the mobile phones. And in this application which we have built, you can prove that you are in a particular state, you're in a particular country without exactly sharing where you are. So think of you're going to Def Connect and you want to share that, yes, I am at Def Connect, but I don't want to share with side event or like, am I at the main stage or where am I? So you can use this particular geolocation thing out there. The other thing is proof of secure media, and this is the whole ideology behind building this project was AI is coming. A lot of deep fakes are destroying the markets. We have seen the whole bunch of fake videos, fake photos coming in, and there was no way to verify if actually a photo was taken by real device. So the second example, the proof of secure media, how it works is right now it's only on iPhone because Apple has something called a secure enclave inside it. And how it works is whenever you install the application that you have built to your iPhone, it will generate a unique key pair, and the private key is always stored on the secure enclave, so that no hacker, no one can actually get the private key out of it. The only way to get your private key is to break your phone, and after that, you cannot take any photos. So that's the safest way to store your private key. And this secure enclave is even used for your face unlock and all those things on your iPhones. Now, what happens whenever you take a photo with this application which we have built? it automatically gets signed by that private key. And then anybody in the world can verify. There are two verification stages for this. That if the photo that I'm watching, or of the video I'm watching, or the photo that this guy is showing that he has captured was actually signed by a private key, first of all, like we will have the public key verification. And then the second stage is this public key or private key is actually generated inside the secure enclave or not. So there are two kind of verification, and if both the things passes, it means that yes, this particular photo was actually generated by a valid iPhone, and it's not a deep fake. So that's a way to stop it. And alpha to all of you guys, if you're going to Def Connect, if you will be around there. So we are launching a kind of social campaign using both of it with some incentivization as well. So stay around, look for tweets from zkV, and maybe you can be a part of that as well.
Are you in our Telegram group? Maybe you can share the details there too. I know that a lot of people gonna go the connect here. Maybe they can
Sure,
help them.
sure,
Yeah.
sure. Melissa will be there, so she'll be taking a lead into all those efforts. Yep,
All right,
sure.
perfect.
I'll do that. Sure. Cool. Yep. So that's a whole review of what is zkVerify, why we are there, why people need us, how our things work. Uh, we have tried to make the DevX kind of easy. So we are always open to feedbacks. If you want to build something on zkVerify, ping me, Melissa, anyone in the team. We're happy to help you. If you have any feedbacks, if the DevX is not good, improve something, please ping us. We'll be happy to uh, listen to what you say. And yeah, that's it. That's a whole lecture on what zkVerify is. Yeah.
Thank you very much. It was an amazing lecture. If you have questions, people, this is the right time, I believe.
Yes, can I go with a question? Yeah, thank you for the presentation. On the last example that you gave, proof of secure media, I wondered what's the guarantee that you give when someone take a picture with the iPhone, that the picture actually comes from the iPhone, like there is no secure channel between where the picture is taken and the secure enclave, right?
Yeah. So how it works is whenever you take a photo, and as I told, we have a private key involved in this whole process. It signs the content of this photo, and then it is embedded inside the photo itself. So some pixels of the photos are changed, are kind of played with, and we do keep the signature of that photo inside that photo. And if I want to verify if this photo was actually taken by an iPhone, what I can do is I can extract that signature pixels from this photo, and then from that I can verify the ZK proof out of it. And the ZK proof verifies that this photo was actually signed by a private key, uh, for which I have the public key. And then Apple has a service called as App Attest. If you want to dig more into that, what App Attest enables you to check is if this particular private key or public key was generated for this app or not. So if you are using the app that we have developed, whenever you generate a new key pair, a private or public key, along with the key pair, you'll generate an attestation out of it. So which I can always check if this particular key was generated through my phone or through my app or not inside an iPhone. And then when I take the photo, I check the signature that if this photo was actually signed by that key pair. And then I verify that this key pair was actually part of my app, not any random app or any other source. It is actually from an iPhone or not?
Okay. Yeah, so you can't externalize but you could do the verification outside the iPhone.
Yeah, yeah. So only the proving part happens inside the iPhone.
Yeah,
The
yeah,
verification
on
can
the
be done anywhere.
okay. And is it the same with all types of things that we can prove? I haven't had the time to check the geolocalization, but it's the same concept that you need to have the prover inside. I don't remember the example, but you always have to have the prover along on the same system that
Yeah,
the data you
yeah,
want to prove.
yes. That's a basic way to do it in a private level proving stuff. But if you explore more about zkVMs, I'm not sure if those are explored in this course or not, but zkVMs are very, very computationally like it's very expensive to create a zkVM proof. And normally it's not meant for client-side proving. So people do it in like huge CPU servers. So uh, companies like SP1, RISC-0, they have like bunch of GPU servers running and people ask them to generate a proof for them. So there, yeah, it depends on your application, what you want to do. You try to do alongside that.
So for the example of a picture, how long does it take? Is it costful?
No, so we are not using zkVMs over here.
Yeah.
So we are using the
Yes, you
Groq
don't need.
16 proofs only. So it's
Okay.
like take 2 seconds to generate a proof.
Okay. Okay. Thank you.
Do we have any other questions?
We have one questions
On
in
the
the chat.
Oh,
Yeah, so on the scalability side of things at zkVerify, we do have a cap right now of around 8 million proofs a day. And we want to extend it a lot more. So we are building few parachains of zkVerify. Think of it like as child chains of zkVerify for each proof type. So instead of having all the as it is right now this parent chain will have small child chains which can handle specific proof types. And that basically gives us the power to do a lot more proof types or like a lot more proof than we have right now. Sure.
I have a question.
Sure.
Like you mentioned in the architecture of zkVerify, that when the relay aggregated proof receipts like eventually are added to the Ethereum blockchain. But you also mentioned in the starting of the lecture that zkVerify is a layer one app chain. So, like, if the proofs are eventually adding to Ethereum, shouldn't it be like an L2?
So we are not adding proofs to Ethereum, we're just adding the hashes to it.
Oh, okay.
So we are not submitting the whole proof to uh, Ethereum or any other chain. And like, so the point of L2 was like it is converted only to one chain to say, but we wanted to be chain agnostic. We don't want everything to just happen on Ethereum, for example. So building an L1 help us to connect with any chains we want to. And obviously we don't submit all the proofs and all the proof details out of it. We just submit a hash of the proof. That's it.
Okay, got it. Thank you.
Okay. There's a question in the chat about will the parachain can be an overhead for the infra? So it will not. It will actually make it more scalable. That's because instead of one chain doing everything, we'll have multiple small chains handling specific proof types. And because of that, the block times can be low for some proof type which are not very computationally expensive. For example, Groq 16. So right now it's 6 seconds, but we can lower it down to like 1 second or 2 seconds. While it is more efficient because the same block space, for example, 50 MB, is specifically meant only for Groq 16. Right now it is for everything, SP1, ultra plonk and everything. But when we do this parachain wala stuff, then it boils down to every specific chain doing a specific proof type. So more block space, less computation time, it's more scalable.
do we have any other questions? I think that's all for the question. Thank you very much for today's session, for the both theoretical part and the practice part, demo part. And I believe we have shared Arman's social in the Telegram group. If not, we can, so that if you have any questions, you can ask directly to him. And yeah, thank you very much. It was an awesome session.
Thanks a lot. Thanks for hosting me around.
We're really happy to have you here.
Thank you. So probably see you on Wednesday as well, right?
See you.
Yeah, see
All
you.
right.
Take care, please.
See you.
Bye bye.
Bye-bye.
To just
Bye bye.